All right, buckle up, because today we are diving headfirst into some seriously mind-blowing physics.
Sounds exciting.
It is, trust me. You guys sent over some incredible research about ultra-high energy cosmic rays. And get this, the possibility of using them to hunt for theoretical particles. We're talking next-level science here.
Yeah, definitely pushing the boundaries.
Before we get ahead of ourselves, though, let's break this down a bit. We're looking at a scientific paper that's all about these superpowered cosmic rays and something called neutral leptons, specifically something called a right-handed neutrino, whatever that is.
Right-handed neutrinos, huh? Sounds intriguing already.
To start us off, can you give us a simple explanation of what UHECRs even are, and why are they so important?
Okay, so imagine, right, a cosmic particle accelerator, but it's millions of times more powerful than anything we could ever dream of building here on Earth.
Millions. Whoa.
Yeah, millions. And that's essentially what we're talking about with ultra-high energy cosmic rays.
Or UHECRs for short. So we're talking seriously powerful stuff.
They're these particles, absolutely bursting with energy. And they're constantly bombarding our atmosphere from, well, who knows where, the furthest reaches of space.
So picture this, like a tiny subatomic bullet. But instead of lead, it's packing more energy than a rocket ship.
That's a pretty good analogy.
It's mind-boggling, right?
It really is.
Yeah.
And what makes them so important is that by studying what happens, when these UHECRs collide with particles in our atmosphere, we get this amazing opportunity
Oh, okay, see.
to unlock secrets about the universe.
Wow.
Secrets we wouldn't be able to even dream of accessing otherwise.
So we're using the universe as our own giant laboratory.
Basically, yeah.
Yeah.
It's a pretty cool lab, if you ask me.
That's amazing. Okay, that makes sense. But this paper takes things a step further, right? It dives into how these incredibly powerful particles might help us find something even more mind-boggling.
Oh, let's hear it.
These neutral leptons. And in particular, something called a right-handed neutrino.
Now, that does sound like something straight out of science fiction.
Right.
But hey, sometimes science fiction becomes science fact.
True enough.
So let's start with neutrinos in general.
Okay.
Imagine a particle so small, so elusive, that it can pass through entire planets.
Entire planets. Get out of here.
I'm serious. Like, they just zip right through, no problem. That's a neutrino, a ghost particle barely interacting with anything at all.
Okay, so we're talking something that makes a ninja look like a bull in a china shop, right?
Exactly.
In terms of stealthiness, I mean,
That's a good way to put it.
but if they're that hard to detect, how do we even know they exist?
It's true. They're incredibly difficult to pin down, but not impossible. We've got these sophisticated detectors, right?
Okay.
And they can pick up the faintest traces of their interactions with matter.
Wow, that's incredible.
And this is where it gets really interesting. We've actually observed neutrinos that have traveled through the entire Earth.
Hold on, wait, I thought you said they barely interact with anything. How can they pass through an entire planet?
That's the million-dollar question, isn't it? That's the mystery. Our current best model of particle physics, the standard model, suggests that they shouldn't be able to travel that far through matter.
So something else is going on.
Something else is going on, something that the standard model doesn't account for.
Okay, now you've got my attention. So this is where these right-handed neutrinos come in.
You got it. This is where we dive headfirst into the realm of hypothetical physics.
All right, let's do it.
So the paper suggests that a right-handed neutrino, which is a completely theoretical particle, by the way, could be the answer.
Okay.
It would be like a mirror image of the neutrinos we usually observe. And it might just explain these longer-than-expected neutrino journeys through the Earth.
Okay, hold on. Back up a second for me. We need to unpack this whole right-handed thing. What even makes a neutrino right-handed?
All right, good question. It all comes down to a property called spin.
Spin.
Spin. Think of a tiny particle spinning like a top.
Okay, I'm picturing it.
Most neutrinos we've seen spin one way, and we call that left-handed.
Left-handed, got it.
But then there's this theoretical counterpart.
The right-handed neutrino.
Exactly, spinning in the opposite direction.
So it's like the elusive twin that physicists have been searching for, the one that could completely change our understanding of the universe?
Exactly. Finding a right-handed neutrino would be absolutely huge for physics.
Wow.
It would mean that our understanding of the universe at its most fundamental level is incomplete.
That's what makes this whole thing so captivating. But hold on. How could a right-handed neutrino, even if it exists, actually explain how other particles travel through the Earth? What's the connection there?
So, imagine this, right? The right-handed neutrino, it acts like a kind of invisibility cloak.
An invisibility cloak for the UHECR.
The UHECR, exactly. It's as if, for a brief moment, The UHECR morphs into this right-handed neutrino, allowing it to just zip through the Earth practically unnoticed, and then it transforms back, boom, it pops out the other side.
Wow, talk about a cosmic disappearing act.
Right.
That's an incredible concept, but how do you even begin to test a theory like that? These particles are already so hard to detect in the first place.
Yeah, it's a real challenge, no doubt about it.
So how do we test a theory like that? Where do you even begin?
Well, that's where things get really clever. The researchers actually used a program called Tor Runner.
Tor Runner?
Yeah, Tor Runner. And they used it to create a simulation
A simulation of...
how these right-handed neutrinos, if they exist, would affect the way UHECRs travel through the Earth.
Oh, wow. So they're basically running virtual experiments.
Exactly. And they were particularly interested in something called emergence angles.
Emergence angles? Okay, now you're just messing with me. What in the world are emergence angles?
All right, I'll explain. Imagine you're shining a flashlight through a glass of water.
Okay, I'm picturing it. Go on.
You'll notice that the light, it seems to bend as it enters the water, right?
Right, because light travels at different speeds through different things, right?
Exactly. That's exactly it. So the emergence angle, in this case, is the angle at which the light exits the water.
So, like, it goes in at one angle and comes out at another.
Exactly.
Because it got bent by the water. So, are we talking about, like, a cosmic game of billiards here? With the Earth as the giant pool table?
You got it. You're getting it. By analyzing the angle at which a UHECR exits the Earth after its little journey through the planet, we can get a good idea of what it might have bumped into along the way.
So we're looking for those UHCRs that emerge at weird angles, angles that the standard model wouldn't predict.
Exactly. And the simulation, you want to know what it showed?
Do tell, what did it show?
It showed that if right-handed neutrinos are out there doing their thing, we should see more UHECRs popping out of the Earth at these wider, more unexpected angles.
So kind of like a cosmic curveball, sending these particles on a completely different trajectory.
Precisely. A cosmic curveball. I like that.
Haha, glad you approve. But to catch those curveballs, we'd need some pretty incredible detectors, right?
Oh, absolutely. We're talking next-level detectors here.
And that's where GRAND and POEMMA come in.
You got it. GRAND and POEMMA are cosmic detectives.
All right, let's start with GRAND. What's the story there?
Okay, so imagine this. A massive, and I mean massive, network of antennas.
Okay, I'm picturing it.
Spread out over an area larger than some countries.
Seriously?
Seriously. All listening for the faintest whispers of radio waves.
Whispers of radio waves, what are they whispering about?
They're generated when UHECRs interact with our atmosphere.
So it's like having a giant ear to the cosmos, tuned in to pick up even the faintest signals from these incredibly powerful events.
Exactly. A giant ear to the cosmos. I love it.
Okay, very cool. Now, what about POEMMA? How does it work?
So POEMMA, it takes a slightly different approach. Instead of listening, it's looking.
Oh, okay, tell me more.
POEMMA, it consists of two satellites.
Two satellites?
Two satellites orbiting the Earth.
Wow.
And they're looking for these faint flashes of light.
Flashes of light from the UHECRs.
From the UHECRs. Specifically, something called Cherenkov radiation.
Okay, I'm going to be honest, that doesn't mean anything to me.
Don't worry about it. It's not important right now.
Oh.
Just know that it's a type of light that's produced when these super fast particles hit the atmosphere.
All right, fair enough. So GRAND is like our giant ear, and POEMMA is our cosmic eye.
Exactly. You got it.
Both trying to track down these elusive particles.
And both are incredibly sophisticated, don't get me wrong. But for this particular search, for these right-handed neutrinos, the paper suggests that POEMMA might have a bit of an edge.
Oh, really? Why is that? What makes POEMMA better suited for this?
Well, it all comes down to perspective. Because POEMMA is up in space, right?
Right, it's got that satellite view.
Exactly. It's got a much wider field of view compared to a ground-based detector like GRAND.
Ah, I see. So it's like trying to spot shooting stars. You're more likely to see them if you're looking up at the whole sky rather than just a small portion of it.
Exactly. That's a great way to put it. POEMMA's unique vantage point in space gives it a much better chance of catching those UHECRs. The ones that have traveled through the Earth at those wide, telltale emergence angles.
The ones that might suggest the presence of right-handed neutrinos.
Exactly. You got it.
Okay, this is all incredible, but there's another layer to this, right? To maximize their chances of actually observing these effects. The paper suggests focusing on UHECRs that originate from a very specific source.
Oh yeah, I know what you're about to say. You're talking about gamma ray bursts.
Gamma ray bursts. Now, those are some seriously powerful events, right?
Absolutely. We're talking about the most powerful explosions in the universe. Imagine, right, The energy of 100 billion suns.
100 billion suns.
100 billion suns, all compressed into a single blast.
Oh.
That's a gamma ray burst.
Okay, those are definitely extreme, but why are they so important for this kind of research?
Because these bursts, they're like giant particle accelerators. They fling out massive amounts of energy and particles, including those UHECRs we're so interested in, across vast distances.
And the more UHCRs we can observe, the better our chances of finding that one, right? The one that might have interacted with a right-handed neutrino.
Exactly. You've got it.
So it's like searching for a needle in a haystack, but instead of a haystack, it's the entire universe. And the needle is a particle so elusive, it makes Houdini look like an amateur.
That's a great way to put it. But here's the exciting part, even though it's a long shot. If POEMMA does detect evidence of right-handed neutrinos, it would be a monumental discovery.
Absolutely. We're talking about potentially rewriting the textbooks on physics as we know it. But let's bring this back down to Earth for a moment. What would finding these particles actually mean for us?
It's about pushing the boundaries of human knowledge. Right now, the standard model is our best explanation for how the universe works at its most fundamental level. But we know it's incomplete. It's like having a puzzle with missing pieces. Finding those pieces, like the right-handed neutrino, could help us see the bigger picture more clearly.
I love that analogy. It's like finding that missing puzzle piece that suddenly makes everything click into place.
Exactly. And you never know where those breakthroughs might lead. New discoveries in fundamental physics often pave the way for incredible technological advancements down the line.
It makes you wonder what other mysteries the universe is holding back, just waiting for us to uncover them.
Absolutely.
Right.
And that's what makes this research so compelling. It's not just about finding one particle. It's about the potential to uncover a whole new realm of physics. The paper focused on one type of right-handed neutrino, but what if there are others, each with its own unique properties and interactions with the universe?
It's like opening a door to a secret room and realizing it's just the first door in a vast, unexplored mansion.
Precisely. And who knows what wonders we might find as we continue to explore.
Well, after this deep dive, I can confidently say that the future of physics is looking pretty bright, even if some of the particles we're chasing are invisible. This has been an incredible journey. Any final thoughts before we wrap things up?
Just this. Stay curious. The universe is full of mysteries, and it's through that curiosity, that drive to understand the unknown, that we make the most groundbreaking discoveries.
Couldn't have said it better myself. Thanks for joining us on this mind-bending exploration of the cosmos. We'll leave you with this thought the next time you look up at the night sky. Remember that hidden beneath the familiar twinkle of the stars lies a world of invisible particles, pushing the boundaries of our imagination and challenging us to unravel the universe's greatest secrets.